To start this lesson on translational equilibrium, I'm going to remind you of a couple situations that we looked at pretty closely previously in physics, and think about what they mean about sort of forces and movement. So the first case is this one. A 20-kilogram object is suspended by a rope, as shown. What is the net force acting on it? Well, Newton's first law says that objects at rest tend to stay at rest unless there's a net force acting on them. So that would suggest, because this is staying at rest, that there's no net force acting on it. And indeed, we find that that is the case. The net force in this scenario is 0. Now we can look at what the actual forces are. I've got a gravitational force acting down, and I'm going to have a tension force acting up. And I should make sure that I've drawn these the same length, right? Because the net force is 0, both of these should be the same length. They're equal in magnitude, but opposite in direction. Another way of writing this is that Ft equals Fg. Okay, so that was easy. Now let's consider another scenario. Same object as before, but instead of sort of hanging there motionless, it's being lifted up. It's continuously moving upwards at a velocity of 4.9 meters per second. What is the net force acting on it now? Well, before we learn much physics, we might look at this and say, well, if it's moving up, there must be a force acting up on it. A net force, you might even say. But Newton's first law tells us that objects in motion will stay in motion unless there's a net force. So as long as this is staying in motion and keeping the same motion, the same velocity of 4.9 meters per second, as long as it's a constant velocity, there's no need for a net force. Yes, there are still forces. We still have Fg acting down. And something must be lifting this, so we probably still have, we can still call it, maybe it's that same rope that was attached to it before. We've still got an Ft going up. And they are going to be equal in magnitude, but the net force is again 0. The forces are equal in magnitude. And that's true as long as it's moving with constant velocity. Another way to think about both of these scenarios is that if we apply Newton's second law, we have the net force equals mass times acceleration in both of these cases. And because neither of these objects are accelerating, this one over here is just staying at the same place. This one's moving, but it's got constant velocity, so there's no acceleration. That means both of those accelerations are 0. So they go away. And we can say that the net force is equal to 0. All right. Now, because in both of these cases, the net force on the objects is 0, they are said to be in what we call translational equilibrium. There's sort of two types of translational equilibrium, and those are the two types we've shown here. In this scenario, where the object is stationary, but in equilibrium, we say it's in static equilibrium. And in this case, where the object is moving, albeit with constant velocity, but in equilibrium, we say it's in dynamic equilibrium. So static and dynamic equilibrium. And in both of these cases, we found that the net force was 0. And that is indeed what we consider to be the condition for translational equilibrium. In order for translational equilibrium to be happening, we need the net force to be 0. And another way we can think about this, especially if we're looking at a more sophisticated problem where there's forces in two directions, we can think about this as having sort of two smaller conditions. One, that the net force in the x direction is 0, and the net force in the y direction is 0. We can think of it this way, or we can think of it this way. Both of them mean the same thing. The second one just explicitly mentions components, where the first one doesn't. Okay, so let's see how we can use this to solve a problem. Here we have a sign suspended using two ropes, shown in this diagram. The tension in the first rope is 100 newtons. We don't know what the tension is in this rope, and we want to know the weight of the sign. Okay, so as you're kind of used to doing with forces, we're going to start this problem with a free body diagram. And before we start a free body diagram, we have to think about which object we're going to draw it for. Well, there kind of aren't a lot of objects here. There's sort of there's the sign itself, but a lot of the forces that are being talked about, like this force and this force, don't even act directly on the sign. If I drew this, just a free body diagram for this sign, it would look a lot like these free body diagrams up here. And it wouldn't really incorporate any of the information that's going on with these tensions and these angles up at the top. So what I'm going to do here is I'm going to draw my free body diagram not for a specific object, but for a point. I want to choose a point that's in equilibrium and that has all the forces acting on it. And I'm going to choose that point to be right here, where all these ropes intersect. So that's sort of my first step. Do an FBD for a point in equilibrium with all the forces acting on it. Okay, so what is this FBD going to look like? Well, I've got the weight of the sign pulling down. And I've got this tension over here pulling up. T2. And I've got this tension over here. Pulling up. I'm doing a bit of a cheating job here. Normally I would say draw a new diagram just for your free body diagram. This is not a great free body diagram because the body isn't free. I've drawn a bit of extra stuff. I've got the ceiling drawn here. I've got this rope, these ropes drawn. So it's not, I'll admit, I'm not doing the best free body diagram here. But I'm sort of trying to cheat and save a little bit of time because a lot of information is given to us already. Okay, so what I might actually do is just make these arrows a little bit longer because that will give me a little more space when I go to write components. Okay, so I picked a point that was in equilibrium with all the forces acting on it, and I drew a free body diagram for that point. Next thing I'm going to do is break these forces into components. So this guy over here, T2, has an X component and a Y component. And T1 also has an X component and a Y component. And I'm going to maybe do what I can to find the magnitudes of these components. So if this is 55 degrees up here, then the Z rule tells me that this will also be 55 degrees. And then this guy over here will be 25 degrees. So I can call this guy T2 times cosine of 25. And this component, T2 times sine of 25. Over here I've got T1 cos 55 and T1 sine 55. All right. So that was sort of my second step. Which is break forces into components. And now I'm going to use my third step, which is apply the equilibrium condition. Right? Our equilibrium condition, remember, is this guy up here. Sum of the forces is 0, or if I'm working with components, sum of the forces in the X is 0, and sum of the forces in the Y is 0. So we've got to decide, because we're using components, we're going to use this and this. And we should probably pick one to start with. We could start with X, or we could start with Y. In general, it doesn't matter which one you start with. If you start with the wrong one, sometimes there's a wrong one to start with, you'll just get stuck. And then you go back to the other one to kind of get unstuck. So let's just do them in order. Let's start with X first. So the sum of the forces in the X direction is equal to 0. That means this guy and this guy, if I add them together, should give me 0. So let's write that down here. T1 cos 55, and that's in the negative direction. And then T2 cos 25, which is in the positive direction. Equals 0. Those two have to cancel out. I actually know T1. It's 100 newtons. So I can plug that in here. In fact, I could have plugged that in long ago. I could have put it up here and had actual numbers there and there. But it's fine that I'm doing it a little bit later. Okay, so if I rearrange this, I get T2 cos 25 equals 100 cos 55. This guy is just going to be a number, and when I divide it by this, I'll get T2. .287 newtons. I'm keeping a few more sig figs here than I normally would because this is not my final answer. So the thing I am looking for is the weight of the sign. In other words, I'm looking for this FG. That's in the y direction. So let's move ahead and look next at the y direction. So in the y direction, I've got this guy going down, so negative, and these two going up, so those will both be positive, and the sum of them should be 0. They're all going to cancel each other out. T1 is 100 newtons, so I'm just going to put that in right off the bat. And T2 is the number I just found. So this guy is my T1, and this guy is my T2 from over here. So solving this for FG, I could take this FG, bring it to the other side to make it positive, and then FG will be equal to all of this. So I just got to plug that in on my calculator, and that'll be equal to FG. So if I do that, and then round to 3 sig figs, I get FG is 109 newtons. Okay, so what do we do here? We were faced with a problem where we had something in equilibrium. In this case, it was static equilibrium. It wasn't moving. But there were a bunch of forces, we weren't really sure what they all were. So, first of all, we picked a point that was in equilibrium that had all the forces acting on it. That turned out to be this point here, sort of the intersection of all of the ropes. If you can imagine these ropes being tied together, we sort of picked the knot between them. Then we decided to take a components approach to solving this. So we broke all the forces into components, right? X and Y for every force. Then we said, since this is an equilibrium, let's apply the condition of equilibrium, which is the sum of the forces in the X have to be 0 and the sum of the forces in the Y have to be 0. And by applying both of those conditions, we were able to solve for the things we didn't know and ultimately get the answer to the problem. Now let's try this problem a different way. There is, often more than one way to do a problem. So same problem, different approach. And what I'm getting at here is when we said what the condition for translational equilibrium was, we said we could either look at the X and Y directions separately and say that the forces had to add to 0 in both of those directions, or we could forget about X and Y and just look at the forces themselves, whatever direction they have to be going, and say that they have to add to 0. So in our first approach, we looked at this way. In our second approach, we're going to try now, we'll just apply this formula directly without looking at X and Y separately. So let's do our free body diagram again. We're going to start with the same approach. We're going to find a point that's in equilibrium that has all the forces acting on it. That'll be this guy. We'll draw an FBD. So I've got FG going down. I've got T2 going up like this. And I've got T1 going up like this. Again, it would be probably better if I drew this free body diagram separate from the diagram I was given. It can get a little confusing seeing this extra stuff drawn here, seeing this rope drawn, seeing the ceiling drawn, seeing the object drawn. But I'm not going to split my objects into components. So my step one was kind of the same. Right? Back here, I did an FBD for a point in equilibrium with all the forces acting on it. But when I get to step 2, instead of breaking the forces into components, I'm going to skip that and go straight to step 3, my equilibrium condition. But I'm going to use the original equilibrium condition, that the sum of all the forces is equal to 0, without worrying about X and Y. What that means is if I take all of these vectors and I add them together, head to tail, as you add vectors, I should get 0, meaning I should get no resultant, meaning I should get a closed loop with no gap at the end. Okay, so let's do that. Let's draw all these vectors head to tail, forming a closed loop, showing that the sum of all those forces is equal to 0. There is no resultant. It doesn't matter which one I start with because we can add vectors in any order. I'll start with FG. Okay, here's my FG. Then I'm going to do T2, just heading up in this direction. And then I'm going to do T1, which is heading up a little more steeply up and to the left. And remember, because they all add to 0, I should get back to where I started in my triangle. All right. Now let's try and put some angles in here. So we know this 25 degrees here, which would be sort of like this angle here. Okay? And we know the 55 degrees here is going to be like what? That would be like this angle here. So what I'm really trying to do here is I'm trying to solve this triangle. The question's asking me for the weight of the sine, which means I'm trying to find the magnitude of FG. I'm trying to find the length of that side of this triangle. So what do I need to do that? Well, I know the T1 is 100 newtons. That's given in the problem. If I know one side, if I could find a couple of angles inside this triangle, I should be able to solve the triangle and find everything else. So let's see what we can do. All right, I'm realizing that I've got a bit of a Z pattern here. And so the Z rule tells me that if that top angle is 55, then this one down here would have to be 55 degrees as well. And down here in the bottom corner, I've got a right angle triangle. So that means because the two non-right angled triangles in a right angled triangle have to add to 90, if this one is 25, then the opposite angle should have to be 90 minus 25, which is 65. So now I know this whole angle in the triangle is going to be 55 plus 25. And I know this angle in the triangle is 65. So because I know two angles and one side, I'm pretty confident I should be able to solve this thing. So what tools do I have at my disposal to do this? Well, it's not a right angled triangle, so I can't use Pythagoras, I can't use SOHCAHTOA. Cosine law is usually really nice for finding a side, especially if we know the opposite angle, which we do. But cosine law sort of requires that we know both of the other sides, and we don't know that. So I think maybe sine law is going to be the best way to go here. So I'm going to pair this angle with this side. That gives me my one unknown, FG. And then I'm going to pair this angle with this side. That gives me two things that I do know. And I'll use those two pairs in my sine law. Okay, so if I rearrange this and solve for FG, I get 100 times sine of 80 over sine of 65 equals FG. And if I round that to 3 sig figs, I get exactly 109 newtons. For FG, which I'll remind you is exactly the number we got before when we solved this using components. So two approaches to solving this problem. One where we break every force into x and y components. And then we look at the sum of the forces in the x direction and in the y direction, and we basically just do some algebra. Not a lot of trigonometry going on here. That's the component method. The other approach is where we don't look at components and we keep the vectors going the direction they're actually going. And instead of saying the x ones have to add to 0 and the y ones have to 0, we just have to add to 0. We just say all of them have to add to 0. So if I put them all head to tail, I'll get back to where I started. Then we're left with a bit of an uglier triangle, but we have the skills to solve it. We go ahead and do that. And then we don't have to worry about sort of doing things twice, once for the x direction and once for the y direction. And both ways, we got the exact same result. Now, I'll say you're welcome to use whichever of these two methods you prefer, the component method or the vector addition diagram, which is what I would call this method up here. Probably going forward when we do examples, we'll mostly use the components method. So that's one that you might want to be more familiar with. But there are times when the vector addition diagram is going to actually be easier for certain problems. Every student's going to have one method that they kind of prefer, and I invite you and sort of allow you to lean on whatever method is your preferred method. But I would advise you to be able to understand both methods. So if we get to a problem where one method works quite a bit better than the other, we can do that, and you'll be able to follow along.